So test grades are now up. There is a little thing, which is the TA said that after he had done everything, he thinks he might have messed up grading 5B. So I have to go back and double check all of those. So your grade might change by 2 or 3 points, one way or the other. So sorry about that. Also, looking forward, next Thursday is again test because I said now it's every other week. So quiz today, test next week, quiz the week after, sort of the test after. Today, all we're going to do is just a few examples from 3.4. In some ways, leaking into 3.5 and 3.6 because 3.5 is just the same thing except volume, which means instead of integrating a function over a region, we're integrating one over the region. So it's actually simpler. So as I have in the chat, now that more people are here, besides staying on the Collaborate Ultra during the quiz, if you want to actually ask me a question as opposed to type it in, I have the Zoom session, which I'll put at the end so that if it's buried by a lot of comments, you can see it more easily. It's one or the other. Okay, so 3.4. So let's integrate a function, and might as well make it simple because we're not going to actually do the integral, over start with the basic one I can actually draw. So we want to integrate a function over a three-dimensional region. As I said, if you want to think of this, you can imagine that the function is the density. And so when we integrate over the region, we're going to get the mass of the three-dimensional object. So this one I do because it's one of the few I can actually draw. So just put in the 3 points, 2, 0, 0, 0, 2, 0, and 0, 0, 2. And you get the triangular shaped region. So it's the solid enclosed by that triangle and the three axes planes. So the xy plane, the xz plane, and the yz plane. So for this, the two steps are first, and this one I'll break up into two places, but you don't have to, is what we're looking for is we're going to integrate the function, and let's do it dz, dy, dx for now. And what we're looking for is similar to 1 and 2 dimensions. We're looking for the smaller function to the larger function. So here it's pretty obvious that the lower function is just the xy plane, so what, z equals 0, and the thing on top is the plane, which we just have to solve in terms of z. So the inside integral is similar to the two-dimensional one, it's just that now we have one extra variable. The part where it gets more complicated is now what we need to do is look at the projection of that thing into one of the planes, xy plane or xz plane or yz plane, and use that to figure out what the limits are for the outside integrals. In general, that can be hard, the picturing, but we don't, in this text, do any real complicated ones, so it shouldn't be too bad. So the idea is here, what I want to look at is, since I'm starting with dz, I want to project into the xy plane, and the two ways of thinking about that is either think of looking at it straight from above it and see what it would look like, so pretend it's two-dimensional, or to just squish it down into the xy plane and see what it is. And here you can actually see it, right? There it is right there. It's that triangle. So if I bring it down, and that happens at the bottom, so when z is equal to 0, So it becomes x plus y is equal to 2. So let me call this r. And now once we're here, it's just like what you're going to get on the quiz. So let me ask, so what are the limits here? So what are the limits for the middle integral? Right, 0 to 2 minus x. And again, bottom curve and top curve. And what are the limits on the outside integral? 0 to 2, because this is the point 0, 2. And as I said, if you want to think of this as something, if 2x is the density, integrating that would give the mass of that solid. So there's the basic idea. The smaller curve to the larger curve, except in 3 dimensions, project into one of the planes, coordinate planes, and then use that to fill out the outer 2 limits. So any questions on this? Okay, so the second one. And again, make it a nice simple one. Okay, so here again, let's integrate something over the region bounded by, this will be a cylinder, just the xy plane, and then the the xz plane, sorry, the xz plane, and this plane here. So I attempt to draw it. So we have the top half of the cylinder. Lovely half cylinder. And then we have, it stops at the xz plane. And now try to do the plane, which goes through the point negative 4, 0, 0, 0, 4, 0. And so it goes from here to here, say, and it's going this way. So intersects in a kind of weird shifted circle. So in some ways, the things that you should be able to draw are fairly basic things. For example, here it's a cylinder, which is just the x squared plus y z squared equals 4 is just a circle. And then y can be whatever you want, which means you just let it go as far as you want. And for a plane, we know that to draw a plane, we need 3 points. So 3 points are negative 4, 0, 0, 0, 4, 0, and 0, 0, 4. But in general, I'm really bad at this. So I have an app on my phone that lets me draw 3-dimensional objects where you just put in the functions. the important thing, which is not obvious from my picture because it's not that great, there are a bunch of, I forget, mine is called 3D calculator or GeoGebra, but there are a bunch of them. So 3D calculator, I think, is what mine is called. So this, you can see, unlike the last one, the projection into the XY plane is, to me, not obvious. It's part of, if it was just the similar from the XZ plane to, say, y equals 5, it would just be a rectangle. But with this, it's not obvious how that gets into it. On the other hand, the important part is notice the plane, since this is the point 0, 0, 2, and this is the point -2, 0, 0. Notice this doesn't hit there at all. So therefore, we're going to want to project into the XZ plane because I know what it's going to look like in the XZ plane, which is just that half of the circle. So if I project this into the XZ plane, I know it's going to look like that. So the idea is there's nothing special about projecting into the XY plane. You can do it whichever one you want. So when I put this together, I'm going to again do the two things because this is going to be another little review for the quiz. So here, since I'm projecting to the XZ plane, I want to start with dy. And since I'm starting with dy, what I'm looking for is what is the left curve and what's the right curve. So on the left, what do I hit? That should be pretty obvious. I'm just hitting on the left. I'm just hitting the XZ plane, or in particular y equals 0. And on the right, I'm hitting the, again, not completely obvious from my picture, but I'm hitting the other plane. And so I'm bringing this down, where I just have to solve for y. So y is equal to 4 plus x plus z, yes. And now, given this, given that that's a half circle, what coordinate system am I going to use? Which is why I'm not really bringing much down yet. Right, so I would probably use polar coordinates. And the way I've drawn it, z is in the place of our usual y. So we have x is equal to r cosine theta. But now z is equal to r sine theta. So when I bring it down, z becomes 2r sine theta. And I convert, what do I always get with polar coordinates? So the dy is going to stay as it is. dz dx is going to become dr d theta. And right, I also get an extra r. No, that, I'm not sure if that was a stray mark, if I was going to start writing, but yeah, there's no negative there. I think I was going to write something and then stopped. Sorry about that. So this is nothing. And this stays the same. And now I have to rewrite both x and z, so this becomes a messy integral. I probably really don't want to do polar coordinates. but it does make the outer integrals easier. I convert all the x's and z's, y stays as it is. So that's a 4 plus r cosine theta minus r sine theta. And what are the limits for the outside one? This is where it at least gets easy. The r goes from, so the middle integral, the limits are the, oh, so you're giving me the outer one, that's fine. So 0 to pi and 0 to 2. Okay. So any questions on this? Again, the same idea, which is we're looking for the smaller to larger. It's just that in this case, since we want to project into a different plane, now we're doing left and right. Whereas if we start with x, then we want the back to the front, smaller to larger. So any questions on that? One more. So we're going to find the volume of the solid bounded by these two. So try to draw it. So we have the paraboloid that I can certainly draw. And then I also have the paraboloid going down. Try to draw it. So let me redraw it from the front. If I drew it, I would get this. And by from the front, for example, it means at x equals 0 or something like that. So again, let me do it in the two pieces. We'll get the projection in a second. So here we're doing volume, which means we're just doing 1. And let me ask, what is here the bottom function? What is the top function? The bottom function is this. So the 2 minus, the bottom is x squared plus y squared, thank you. And the top function is the 2 minus x squared minus y squared. So here, there's the slight extra, which is from the top, both paraboloids look like circles. Just one is getting bigger as you go up, one is getting bigger as you go down. And so the question is, where is it at the biggest? So how are we going to get the projection? So it's certainly going to be a circle, as I said. The question is, where is the circle going to occur? Or how do I find where it occurs? In some ways, you can kind of see it here in this my front. Right, so this is what we're looking at. Right, so you can kind of see it here, which is you can see the biggest is going to be where they intersect, which is not the scale. So if I set the two equal, the z equals z, I get x squared plus y squared is equal to 2 minus x squared minus y squared, which gives me x squared plus y squared is equal to 1, because I get 2x squared plus 2y squared is equal to 2, divide through by the 2. So there's the projection. again, like the last one, since this is a circle, we probably want to do polar coordinates. And so I'm going to redo these inside limits. So what does everything become? The bottom limit becomes r squared. Top limit becomes 2 minus r squared. I still have the 1. I'll put that there just to show I'm not changing that. But then, as with the last, I'm going to get the r as I change the dy dx to dr d theta. And now back to polar coordinates, stuff on the quiz, which is what are the limits? Start with the middle one. So 0 to 1 for the r, because it's just circle. And for theta, the limits are all the way around, 0 to 2 pi. Officially, I'm kind of jumping through 3 sections here because 3.4 is looking at just integrals in 3 dimensions, which obviously we're doing. 3.5 is looking at volume, and the only difference between that and 3.4 is instead of integrating a particular function, we're always integrating 1. And part of 3.6, which is cylindrical and spherical coordinates, and this is we're using cylindrical coordinates, which just means we're leaving in cylindrical coordinates, you just leave one of the variables alone and then change the other two to polar coordinates. So in theory, this is a problem that comes up that uses some material in 3.4, 3.5, and 3.6. So you can see those 3 sections are fairly similar, except for we're going to have to do spherical, and obviously we're not going to start that today. So any questions on this? Okay, so let me try one more. Look at 5 minutes. And we didn't make another volume. So let's find the volume of this thing. And this one I'm not going to draw. This is just a cylinder, and I'm even bad at drawing cylinders. Cylinder that goes straight up to the z-axis. So what I'm going to do is I'm going to say, let's look at from the front. So from the front, and from the front again means I'm looking at x is equal to constant, so say z, well, y and z. From the front, it just looks, the cylinder just looks like a rectangle, where this is the line, this is y is equal to 1 and y equals negative 1. Oh, actually, I should have not, since I'm doing x plus z, sorry. I should look from the side. X, x, x. And then draw x plus z is equal to 1, which notice gives us that. And then we also have z equals 4, which is somewhere up here. So here's our region. So this way I can do it all in one. What is the projection going to be? What does it look like from the top? Well, so remember from the top, so this, if I start doing it out, so this is a cylinder, so if I start doing this type of thing, it really is like that. So yeah, circle. And again, the important part is here, this is this simple version, which is we get the whole thing because when z is equal to 0, we get the full circle. So if instead the line came and hit here, it'd be more problematic. We just get part of the circle. That would make it more complicated. I said, luckily, we don't get any of the, in this text, any of the more complicated stuff. So it's just the x plus y squared is equal to 1. So let's go through the whole thing. This one I'm just doing in 1. And since we're doing volume, again, we're just doing 1. Yeah, I guess I will do it in 2. Because we're going to do probably polar coordinates again. So here is the bottom limit. Notice this region. Right. So it's the right. So we're using the x plus e equals 1, so we solve for z, and we get 1 minus x. And then the upper limit is 4. And then we're projecting into something that's a circle, so we probably want to use polar coordinates. So therefore, 1 minus x will become 1 minus r cosine theta. We'll get the extra r. And again, you'll see these are all fairly simple ones, kind of on purpose. Here the limits are, I think, same as the last one. The limits for the middle are 0 to 1, and for the out they are 0 to 2 pi. So like the last one, this again uses material both from 3.4 and 3.5 and 3.6. Triple integrals, volume, and cylindrical coordinates. So let me stop there. It's now right about 2. So any quick questions on this? Right. So in particular here, if I project it into the xz plane, it probably would just be a rectangle. And then I could just use that. Right, and then I wouldn't use polar coordinates. Of course, then it gets more complicated because now you have on the left and the right, the left would be this would be the circle, and the right would be the plane, but only for part of it. Actually, no, the whole thing. Right, only for part of it because the left and the right change. I'm pointing to the wrong side of this circle. So we don't really, so we could project it, and it would, in some sense, be a rectangle if we project into xz plane, but it makes it more complicated in setting up. Right. So any other questions on this? Okay, so let me stop recording.